Hi, I'm Chris,
And I'm Terry.
and today we're going to do a follow-on lecture from the Principle 3 lecture from the NEF. And today it's all going to be all Terry, so it's really just the Terry show. Take it away, Terry.
All right. So the plan for today is to actually build something. So we've spent a lot of time sort of laying down the groundwork of, well, here's the basic components that neurons are really good at implementing. But I think one of the really big challenges that comes up is, okay, fine. We know we've argued that neurons are good at representing vectors. We've argued that connections between neurons are good at computing and transforming those vectors, computing functions on those vectors. And we've argued that the recurrent neural networks are really good at implementing differential equations. So that's principles 1, 2, and 3. But putting that into practice is a whole other game. So like, okay, how do I actually sit down and build a little brain that goes and does something using these components? So that's what today is for. So the challenge for today is we're going to build a little critter. Some of the basic parts you might want to need for a brain. We want to have some sort of input, we have some sort of output, some sort of memory, and some sort of decision making. So the particular challenge I'm going to put out here is sort of the simplest brain that I can come up with. And the idea is we're going to have two inputs. One of those inputs is going to be some sort of desired velocity signal or something like, oh, hey, there's food over in that direction and in that distance. You should probably go in that direction. You could think of that as sort of, I don't know, smell or hearing or something that tells you that sort of distance. And I've got another input as well, another sensory system that is, we're going to call this a fear indicator. We're going to call this, is it safe right now to go and find that food? Or should I not, should I not be finding that food? So we're going to, those are our two inputs. Our output is just what direction we're going to go, and the actual behavior that we want this brain to implement is, well, if I'm not afraid, so if the fear indicator is low, then go in the direction that the food is in. Okay, so if the fear is low, then, oh, hey, look, there's food over there, just go get it. So I don't know, maybe if it's dark, if there's no predators around or something like that, then it's safe to go and find that food. But if the fear indicator is high, I don't know, so it's either, maybe it's bright out, so there's lots of vision, or so you might be seen, or maybe you're hearing predators, something like that. If that fear indicator is high, then don't go towards where the food is. Don't go there. Instead, go back to where you started from. So that's going to require a little bit of memory, right? Because we've got to find out, figure out where we're going or where we've been, and so we've got to actually go back to where we started from. And there's a little bit of decision making there because I've got two different things I might want to do depending on the task. Okay, so this is sort of the bare minimum simple creature, and I want to use this as an example of, let's go ahead and build a model using Nengo. We've just started Nengo fresh. I'm going to start a new file. I'm going to call it critter. And then I'm going to delete everything. All right, so how are we going to make this work? More space. All right, so what I generally find when building cognitive models is I'll tend to start by at least defining the inputs and outputs because they're usually relatively clear given the tasks that I'm building. So let's start with that that input that is what direction I should go, what direction the food is in, or where the food is relative to me, sensor like that. Okay, so we're gonna have a group of neurons that goes and represents that. And then the big question is, well, what is this vector that they're representing? And we've got a bunch of different options here, because if I want to represent a direction and a distance, then I could say, okay, I don't know, there's an angle and a distance, so we could do some sort of polar coordinates. So what we're actually going to do here is we're going to say, okay, let's just be even simpler than that. Let's just say it's an X and Y distance relative to where we are. Okay, so this is just dimensions equals 2. And so 0, 0 is going to mean food is right where I am. There's actually a bunch of good reasons to choose XY coordinates as opposed to R and theta. One of the biggest easy ones that jumps out is that if you decide to represent an angle, you've got this weird discontinuity at 360 degrees or at 2 pi radians, where, or if something is behind me, I can either call that, well, it's positive 180 degrees away from where I'm facing, or it's negative 180 degrees away from where I'm facing. That means the same point. It's this weird discontinuity. I'm going to stick with XY values. And then there's reasonably good evidence that that's also what brains do. We're going to need some sort of input that is going to be fed into this. And we're going to just set it up so that we can control that with sliders. If I had a more complex environment, some sort of simulation of an environment, then we would write some Python code there to grab data from an environment and feed in the actual data. Again, for simplicity, we're just going to simulate the environment ourselves by moving sliders around. And we're going to make a connection from stem food to food. All right, so in theory, this is sort of just a group of sensory neurons where I can go ahead and pull up a slider and pull up an XY value. And I can say, okay, hey, look, there's food right where I am right now. Oh, there's food over to the right. Oh, there's food up here. There's food over there. That's going to be the idea for this group of sensory neurons. Okay. All right, so that's one sensor system. Let's go on to the motor system, to the output system. And again, if this, we've got to make some decisions about what the representation is on our output. If we were having sort of a really, some complex robot that Nengo was controlling, then we would have to have our output be whatever commands are supposed to go to that robot. Or if we had some sort of simulation environment that we were using, then the output would be whatever commands that simulation environment wants. Again, for simplicity, we're just going to ignore all of that right now and say, all right, my output is this group of neurons here. And it's just going to be, again, a two-dimensional vector, which is just the velocity that I'm going to move in X and Y directions. Okay. So it's just, again, if this one is outputting 0, 0, that means I'm staying still. If it's outputting 1, 0, that means I'm heading off to the right, and so on. We have some input, we have some output. Now let's start building up a little bit of the brain on the inside. Okay. And what's the simplest possible thing that we can start with? Well, for now, let's just ignore that whole decision-making process. And the simplest thing that we could have done is simply say, hey, whichever direction the food is in, go in that direction. That would have been the simplest thing. So let's just, as an example, set that up. It's food to motor. All right. So that's just, hey, I don't even have to compute some function on it. I just simply say, hey, whatever direction the food is in, go in that direction. So now I can just say, all right, if there's food over here, then I'm going to go that direction. This is as simple as possible. And this is just the communication channel. We've sort of seen this sort of example before. I'm not sure if we've done it in 2 dimensions before, but it is just computing the identity function. Nothing fancy yet. But that isn't quite the task that I described. Well, the task that I described is at least going to say, hey, I should only go do this if I'm not currently afraid. All right, so first thing I'm going to need some sensory input that indicates that fear indicator thing. Right? So I've got fear. One thing that sometimes jumps up when I'm doing this is you'll notice that when I'm creating these groups of neurons, I'm needing to define a number of dimensions. Well, needing to find a number of dimensions and a number of neurons. Number of dimensions is usually just defined by the task. It's usually just sort of, okay, I need to represent two things, an X and Y value. Fine, I need 2 dimensions. Or I need to represent fear, that's 1 dimension. The number of neurons is a little fuzzier. And exactly how to pick that initially, certainly if there's biological data you're comparing to, then you can actually say, oh, okay, well, how many neurons does the real creature use? At least you can do that for small creatures. So like the neural integrator in the goldfish eye is 40 neurons, whereas in humans, it's, what the hell is it? It's like 100 neurons or something, right?
It's about 2,000 neurons.
Oh, okay.
Yeah.
Yeah. So sometimes you actually have good data on that. When I'm initially building a model, I usually don't worry about that initial good data and leave everything with defaults. And what I generally get into the rule of thumb is, well, as I adjust this number of neurons, it's going to become more accurate, but it's also going to slow my simulation down. So I usually pick some sort of, hey, for 1 dimension, I'll use 50 neurons or maybe 100 neurons, because that's going to give some amount of, here, let's actually plot this. So when I look at the value here, I'm getting some amount of jitter here, right? There's some amount of noise around 0. Okay. And as I increase this number, I'll get less noise. All right, so that's a little bit less. And it's vaguely linear in the number of neurons. So, so as long as I'm sort of happy with the amount of noise that I have for 1 dimension, I'll use 50 neurons. I'm sort of happy with that level of noise. Then I'll usually just sort of be kind of consistent with that. Where it's like, oh, hey, look, if I'm representing 2 dimensions, I'll use twice as many neurons. It's it vaguely keeps the amount of noise about similar, or the amount of error in the representation around similar. So I just get into the habit of doing that, and then what I'll often do is later, once I'm happy with the model, then I can go back and I can say, cool, if I reduce the number of neurons, how far can I reduce the number of neurons and still get good behavior? I can start exploring those sorts of questions.
I don't know if we care, but I guess we actually know the way that the noise reduces is 1 over root n, right? So it's not quite linear, which doesn't matter. I think your point is it doesn't matter for small numbers of neurons effectively, but as you get more and more neurons, you do pay a squared cost in order to reduce noise. Yeah.
Yeah. So basically, yeah, pick 50, pick 100. You will start finding as you get these numbers bigger that it takes longer when you press play, that gear spins for longer. And certainly if you have, like don't do 5,000, that's, well, I mean, 10,000 is sort of the upper end. If you have a very good implementation of Python, stick in this sort of range. It seems to be a reasonable rule of thumb.
I think it's also interesting to point out that for even models as complicated as Spawn, we never have numbers even close to 10,000, right? Maybe on the order of a couple hundred, where we've essentially broken all the populations down small enough that the solution is pretty quick.
Yes, that's a really good point, that even though Spawn has 6 million neurons in it, any individual ensemble, I believe the largest ensemble is actually in the motor system, and it has something like 3,000 neurons, but everything else is like 100, 200. Yep. All right, so we have so we have a group of neurons representing fear. We need some sort of slider or input to this that'll let me control the fear. Fear to fear. And now what we want is we only want to go in the direction of the food if we're not afraid. How the heck am I going to implement that? If I was a programmer, this would be pretty easy, right? Like I would just simply say, hey, look, if this is above, so right, the sphere is between -1 and 1. So if it's above 0, then just delete this connection, right? Just don't have this connection from food to motor. That would sort of conceptually be what we want. Biology doesn't really have access to that as an option. Right. So how are we going to do this? As with the controlled integrator example that we talked about last time, there's multiple different ways we could do this. And each different way that we do it is going to give make slightly different biological claims, right? Which I love that aspect. Implementing it in various different ways, you'll get slightly different behavior and you'll have slightly different biological claims. And this is as a scientist, this is wonderful, because what you're actually doing there is all these different ways of implementing it. Those are different hypotheses, and they should be testable in terms of, well, they're making different statements about what's going on at the biological level, and they should have slightly different behavioral effects. We'll take a look at a couple different options. Okay, so what I need to do is I really want to have this group of neurons to have its input affected not just by this, but also by this. Okay. We haven't talked about having one group of neurons being able to control connections between the group of neurons, so how can we think about it in this case? But it turns out we have talked about something pretty similar to this. We've said that neurons can compute nonlinear functions. That groups of neurons can compute nonlinear functions. And you can think of what I just said, the statement of, if fear is greater than 0, then motor should be 0. And if fear is less than 0, then motor should be whatever food is. You can actually write that as a function. Right. So what I can do, but it's a function of 3 variables, right? It's a function of the level of fear and the XY value in the food. What do I mean? So if I have another group of neurons called, I don't know, do food. Whoops, helps if I can spell neurons. And if I connect the fear to the first of those dimensions, and I connect the food to the other 2 dimensions. Okay, so this is now a 3-dimensional population. Now what I can do is when I make a connection from do food to motor, now I can compute the function that I want to do. Okay, it's a little bit weird. Okay. So what exactly is that function? So this will be, I'm going to define this food function. This is a function, so X is now 3-dimensional. I'm definitely going to get confused as to what those 3 dimensions are, so I'm going to go ahead and define some intermediate variables so that I can see that. So the intermediate variables are going to be something like fear, food X, and food Y. So that's what we're going to break. So X is 3 things. We're going to split those into those variables so I can refer to them by those names rather than X0, X1, and X2. And now I can write my function. My function is, well, if I'm afraid, then don't go anywhere. And otherwise, okay. So that's a function that does the task that I'm hoping for. All right. And so then I can make a connection from do food to motor, where the function is the food function. And this is also a situation where having the graphical display is helpful because this is now indicating to me, oh, right, I've left in this connection here from food to motor. We don't want that anymore. So I'm gonna go ahead and remove that one. All right, so let's make it not afraid. And now I'm gonna say, all right, there's food over there. And it heads off in that direction as before. Food over there, heads off in that direction. Food up there, yay, everything's all good. And now let's scare it. And now it freezes. And you'll notice it's not perfectly freezing, right? It's moving a little bit, but it is certainly not moving in the direction of the food. Okay, so that moving a little bit, that's exactly the, neurons are just approximating this function. And as long as that's a good enough approximation, everything's fine. Okay, so we've got just a little bit now of this decision-making process happening. Cool. Let's go on and do the rest of the task, and then we'll come back and sort of see, are there other ways of implementing that particular function? But what I've just described there is sort of a very general method. So now that we've seen that, let's see an alternate implementation of the same task, just to give an idea of another way of doing this sort of freezing behavior. You would have to add in some interesting biological details if you wanted to have one group of sort of a direct connection from food to motor, and have this other group of neurons be able to somehow stop that connection from doing anything. Can't really inhibit axons. But you can do something like inhibiting these neurons. Now, so for instance, if all of these neurons stopped firing, so all right, so let's go back to, so that was one example. We could also have done it, here's another possibility. If I said make a connection from food to motor, I'm just going to comment out all of that temporarily. There we are. So we're back to the normal situation. Now, one thing that we could also have done is said, well, hold on a second. If all of these neurons were inhibited, if all of these neurons were just, we somehow had some external signal that just stopped all of these neurons from firing, that would also have the same effect, right? That if these neurons were able to inhibit these neurons, we could also have a similar effect here. We do get an interesting question of, okay, do we really want to inhibit these neurons in particular? Or maybe what we could have done is we could have said, all right, let's have another group of neurons. Whoops, do food is a Nengo ensemble. 100 dimensions, it's 2. And we could have said, all right, let's make a connection from food to do food. So this is similar to before, except I'm now having do food only be 2 dimensions. From do food to motor. Okay. So I've done something similar, except this is now only 2 dimensions. I'm going to inhibit these neurons. The reason I'm going to inhibit these neurons rather than these neurons is if I'm in some larger brain system, it might be that some other part of the brain is also taking advantage, is using the information about where the food is. And if I inhibit these neurons, then that's going to mess up everything that uses this data. Whereas if I make this intermediate group of neurons, then I can just inhibit this, and I'm not messing up anybody else that might be using this. Makes some sense. But now if we want to specifically inhibit a group of neurons, that's something that we haven't really talked about in the NEF yet, right? How do we do that? That's more sort of like normal neural network behavior. That's more like just make a bunch of connections to the neurons and just make sure all the connection weights are negative. Right? So that's a situation where we are specifying the connection weights themselves. We don't want to use this neural engineering framework thing to calculate the connection weights. So we have introduced, like at the very beginning, we saw some syntax like that. So I'm going to, but I'm going to go ahead and use it here anyway, just to see what that's like. And the idea here is you can do a connection from the fear neurons. So, okay, we're going to do two little things here. We're going to say, all right, we need to figure out, should we be inhibiting? To inhibit. And we're only going to inhibit, if x is greater than 0. So if we're afraid, then we are going to do the inhibiting. Otherwise, we're not going to inhibit. Okay. I'm going to now make a connection from fear to the do food neurons. The function is going to be do inhibit. And that's not quite going to work because do inhibit is now returning 1 value, but do food neurons, that's 100 values. That's because there's 100 neurons there. There's two ways I could deal with that. No, let's actually just do it right here, right? So I really don't want to return 1 and 0. What I really want to return is, well, how much inhibition should I be sending to these neurons in these different situations? Right. So I'm going to return, I don't know, lots of inhibition, and I'm going to have 100 of them. All right, that should look a little weird to you, okay? Because I'm sort of mixing both the NEF style, oh, hey, look, I have a bunch of neurons here that are representing fear, and I'm going to use that to determine, should I be sending an inhibitory signal to these neurons or not? Okay. But then on this, when I'm connecting to the neurons, whenever I use this doFood.neuron syntax, that's saying, hey, ignore this whole NEF thing of encoders and decoders. I just want to talk about this as a normal neural network right now. So my target, I'm just referring to as just a normal neural network. And so that's why I have to sort of manually specify, hey, look, there's 100 of these outputs. The sphere is sending things to 100 different components here. And I've said, hey, if x is greater than 0, so if I'm afraid, then send -10 to all of these neurons. So that should be a lot of inhibition to all of those neurons. And otherwise send 0 to all these neurons, so don't inhibit them. A little bit weird. I'm mostly highlighting this as a slightly different, as a way of, yes, Nengo supports totally normal neural network syntax. You can just specify connection weights yourself, and you can do this mix and matching of these components, okay, or of these approaches. Okay, so now we're going to say, all right, there's no fear. Cool. It runs around. It goes and does things. It goes and chases where the food is. And then I can go ahead and give it some fear. And all of a sudden, those neurons are not affecting the behavior at all. Okay. Now, when I went into this, I sort of said, hey, different implementations are making different biological claims. This sort of structure looks pretty similar. So those two different implementations that I showed have very different sort of anatomy in terms of the structure. But if we go ahead and look at the spike patterns, okay. Oops, let's have no fear, right? So right now, all right, so we're getting, some sort of spiking pattern in there. Okay. But then the moment I start giving some fear, those neurons shut off. Okay. And that's very different than if I went with the approach that I implemented before. Okay, so I do it this one. Okay, I say, all right, there's no fear. It's moving around. All right, and then I give it some fear. In this case, all that's happening is we're getting a different pattern of activity in these two food neurons, rather than completely shutting them off. And we're also getting a different sort of, there's also sort of other more subtle behavioral effects, like when I'm afraid in this case, I'm not perfectly going to zero motor movement. Right. Whereas in the other case, it was actually closer to zero. So again, you get this situation of multiple different implementations, give you multiple different biological claims, and slightly different behavioral effects. So, all right. All of that said, and that trick of inhibiting neurons really only works in these cases where, in some case, you want to make sure that the function is returning zero, right? Because inhibiting neurons, okay, that's a way of representing zero, because if no neurons are firing, if the activity is zero, then 0 times whatever decoder you come up with is also going to be an output of 0. So 0 is a sort of a special value, and it's something where you can look out for that sort of thing as you're building up a model. Okay, bit of a digression there into different ways of implementing things, but I think it comes up a fair bit.
I guess it might be worth jumping in and saying again that this is the method we use in Spawn 1.0 anyways, is all this kind of inhibitory routing as opposed to the multiplicative stuff.
Yep.
Although there is lots of multiplication as well.
Yes, especially for this sort of cognitive control, and we've done some interesting work sort of comparing that to the cortex basal ganglia thalamus loop. So there's reason to believe that that something like that might be happening in mammals. For simplicity, we're just going to stick with the first implementation because it's a little bit more flexible, a little bit more general. But if anyone wants to pause the video and play with those other implementations, the code's there. All right, so we have our implementation of part of the task, but now the other part of the task is, hold on, we don't want it to, so right now when it's feared, when it's afraid, it just freezes, which is great, it's making some sort of decision. But what we really want to do is we really would like it to run back to where it started from. And that seems tricky. How are we going to do that? One thing it's going to require is, so the first step in that is it's going to require some sort of memory, because we got to know where the heck we are so we can know which direction to go in order to figure out, you know, whether we're heading home or heading to back where we started from.
Don't you remember, Terry? Last time we built memory.
Exactly. So this, and I think it's worth noting that in the Principle 3 lecture, the dynamics lecture, we sort of showed, hey, look, you can implement any differential equation you want. At least half of the time, it turns out that the differential equation that I want is an integrator. The mathematics of the integrator are simple and linear, and that also means that we know neurons are going to be really good at approximating it. So it's definitely a very safe thing to be implementing. It also turns out to be really easy syntax-wise to write in Nengo, because you almost don't even have to remember all that weird that math that we went through. Yeah, just because it turns out to have that really nice form that we showed. Okay, so let's go build up this integrator.
I think there was a point at one lab meeting where I was known to have burst out, "It's integrators all the way down," or something along those lines, because they really do show up absolutely everywhere. It's quite strange.
Yeah, Chris, very frequently, you know, like integrators just show up absolutely everywhere. It's yeah. So let's build one. And the reason integration is going to make a lot of sense for keeping track of position is if my motor command is some sort of velocity signal, then the integral of my velocity signal, it should be my position. Yeah, so this just seems to be exactly what we want. All right, so we're going to make a group of neurons to represent position. Because I want this to be fairly accurate, I'm going to go increase the number of neurons a bit. We do know that it is going to be two-dimensional. We want this to be an integrator, so we need to make that recurrent connection. position to position. The nice thing about the integrator is that recurrent connection is supposed to approximate the identity function, and that's the default in Nengo, so I don't even have to specify the function. But I do have to remember to specify the synaptic time constant to use. And the general rule of thumb is use something at the high end, so 100 milliseconds there. So that should now be an integrator. Okay. And again, this is one of these situations where you can sort of vaguely intuitively sort of see, oh, of course, if this system has no input, whatever its current value is being sent to it's being sent back to itself. So of course it should be an integrator. Like that just that seems to at least make some sort of intuitive sense. We want to change the value of this integrator based on our motor command. So I'm going to make a connection from motor to position. We're going to use the same synapse. And the one thing that you always that you do have to remember whenever you're implementing an integrator is, oh, right, I do have to make sure that I scale my input. The math that we showed, if you want it actually to be exactly a mathematical integrator, which means if I have an input of 1 for a period of 1 second, then that's how long it should take it to go from an internally stored value of 0 to go to an internally stored value of 1. So if you want it mathematically to be the same as integration, then the transform that you put on here is 0.1. But it is also worth pointing out that really all this is acting on is a scaling factor on how quickly to change this internal representation. If I want it to change more quickly, I increase this number. If I want it to change more slowly, I decrease that number. Okay. All right, let's take a look at this. That's one plot. Okay, I'm not afraid. Just because I'm going to keep pulling this thing down to not afraid all the time, I'm actually going to go in here and say, all right, the stimulus sphere, instead of being a default of 0, I'm going to put in a default of -1. Run that again. There we are. So now my default is -1. And so now what we've got here is a little bit of a memory. All right, so this is where it where it thinks it is. All right, if I say go to the right, the motor says it's going to the right. My position is updating, it's going to the right. I can stop. My position stops updating. I can say go up, it'll go up. It'll stop. If I go left, it'll go to the left. Okay, it's not a perfect integrator, of course. If we had, it will drift slowly, and perhaps you might have seen it drift a little bit. And we can play around with that sort of number of neurons to affect that. Of course, and again, in a real biological systems don't just use their own motor actions. It is one thing that they do use, and there's lots of fun experiments on rodents and trying to figure out how well the rodents can figure out where they are based only on their own movements. And so you can measure how accurate those are. But in a real biological system, there'd be other sensory data that you're using to also try to update your position. Or in a more complex brain, that's what would happen. But this will be fine for now. However, there is one interesting aspect that we do have to keep in mind about this position, and that is what happens right now if I go up. So I'm going up, I'm going up, I'm going up, everything's fine. And why did it go over here? What happened there? And the answer, as is the answer most of the time when being confused about something in Nengo, is it has to do with the radius. This group of neurons is optimized to represent inside this unit circle. As it goes up, let's try, oops. Okay. When it goes up, it's starting to try to represent points outside of that unit circle. Since it's not good at representing things outside of that unit circle, the actual represented value is going to be back in closer to the unit circle. And so that's going to pull it to the right a little bit, and that process is going to continue, and eventually it's going to think it's up there. All sorts of interesting ways to sort of deal with that problem. One is, of course, increase the radius. And so let's go ahead and try increasing that radius. If I now say radius equals, oh, let's just make that problem totally go away. I'm going to say radius is 10. What's going to happen there? What's going to happen there is now it's going to be less accurate. You'll notice this giant blob now, right? Right? And that just sort of makes sense, because if I'm using the same number of neurons to represent a larger space, well, of course, it's going to be, this is, in some senses, a 10 times larger space. So it's going to be 10 times less accurate. So that sort of thing is expected. So you can't just crank up the radius to 10 million and make this problem go away. There's all sorts of other fun things that we could be doing in there. And indeed, some of the early papers on the NEF were looking at ways of building this this integrator memory such that it loops around, such that when you go out the top, it'll come in the bottom. That's sort of one approach. And then this starts getting us very much into the domain of modeling things like grid cells and place cells. And so there's a whole fun direction you can go of saying, all right, how do we make this being something that doesn't have that restriction? But that's like, there's a bunch of fun papers if we want to get into that in more detail. But for the most part, what we're instead doing here is, hey, look, whenever you have some sort of representation, be aware there's going to be bounds on that. Right? And if I need a larger radius, fine, all right, I just need more neurons, which is also a pretty good approach. Okay. So that's going to be fine for now. We've got this nice little position thing. You can go ahead and represent stuff. That's all good. And now, now we have our memory, and now what we need is to say, hey, if I'm afraid, then go back to where I started from. All right, how are we going to do that? Well, that's pretty similar to what we did here. So we're going to do a similar trick. All right, so I'm going to say, all right, I'm going to have this home thing. Again, it's going to be 3 dimensions. The dimensions are going to be, well, first of all, one dimension is whether or not I'm afraid. One dimension, and then the other 2 dimensions are not, instead of before it was based on the food, but the other 2 things I've got to take into account now is, well, what's my position? Fine, so we fed both of the pieces of information we need into this do home group of neurons. Now we're going to need another function. This home function. Again, it's got 3 things in it. I'm going to give them more meaningful variable names. And now we have this, well, if fear is greater than 0. So if I am afraid, what should I do? What direction should I go in? Well, I don't want to go in the position that I'm at. If I want to head back to where I'm starting from, that's the negative of the position that I'm in. And otherwise, return nothing. Right. Go connection from do home to motor, computing the function home function. Oops, function equals. All right. And since we've got both of these 2 things, both feeding into this one group of neurons, we're now relying on the fact that, hey, when you feed in neurons from 2 different inputs, well, the actual value that it's going to represent is going to be the combination of the 2. It's going to be the sum of the 2. Cool. Does that work? Run this. All right, we are not afraid. We are going to head over to the right. And okay, so we're telling it the food is off to the right, the motor is off to the right, our position is updating, everything's happy. There's food up here, off it goes up there, position's happy, and then all of a sudden we scare it. And even though the food is still up there, it heads back to where it's going. And then we say, okay, you're not scared anymore. And then off it goes towards the food. And then we scare it, and back it goes. Yeah. Now you will also notice that it's doing things like slowing down as it gets closer to where it started from. Right? So you'll sort of see it going quickly and then slowing down and slowing down and slowing down. That's because that's actually what we've asked it to do, right? Like since the command that we're sending is a velocity, that would happen. We could make this a more complex if statement and say, we'll just go in that direction at full speed or something like that. That would also work. We can also do simpler things like, oh, I don't know, just multiply this by 10. So just run faster when you're going home. That. Right. Oh, that's clearly, right. And this is exactly where we get into the situation of, maybe that's not that's introducing a lot of noise into the system. No, actually not. Right. So we can get these sorts of unexpected side effects. Although if we scare it now, it does run home much faster than before. And so you get these interesting interactions between, as you change one thing, it's going to affect other things. So maybe you just say, all right, we'll run a little faster, run a little slower. Again, each of these things make different behavioral claims, and so then these become different hypotheses that you can then go ahead and test by going and looking at what the real systems do. Say, all right, scare it, it heads home. And then say, all right, you're not scared anymore, and then off it goes. Cool. So that's the vague process that we often go through when building up a little brain model. One observation that often does come up is, yes, once you start building this, you tend to get these sorts of, hey, look, this thing's connected all over the place and connections going, and you get this big, giant recurrent mess, which tends to be what brains look like anyway. So I kind of like that aspect, that you tend to end up having lots of connections back to themselves. That also means that there's some interesting optimization that you can do once you've built it. So for instance, if you ever notice this sort of, all right, I've got some stimulus, it's going to something, I've got just something, hey, this is all just a feed forward. You can often get rid of these intermediate groups of neurons. So for instance, I could have just had this external stimulus directly going into these groups of neurons here, right? That would be a different biological claim. That would be saying, all right, so right now what we've got is here I have a group of neurons that are only sensitive to the food stimulus, so maybe these are raw sensory neurons. These neurons, I might imagine, the neurons in here are sensitive to both food and fear, both the direction of food and fear, right? So that becomes an interesting claim of, does the raw sensory data come into neurons that are sensitive to multiple things, or does the raw dense sensory data go into neurons that are only sensitive to one thing? But this is certainly a group of neurons where I could get rid of this group of neurons and directly feed this into here without changing the model in any detailed way. So sometimes I'll find that I've got a chain of these things, and then I can sort of collapse those together and sort of say, oh, I didn't need those after all. Chris, anything else jumping out to you for you in that?
So I think the most important observation to me is that you started down a path which gets really hard after a while, which is you've got a couple of different if-then statements, you're trying to make decisions, and you can imagine if you start piling more and more of these in, this just turns into a really big, complicated mess, which would make scaling to something like Spun nearly impossible.
Yes, that is a really good point, that this aspect of having these if statements and whatnot fine for this little creature that has only 2 actions, but imagine that you had 10 different actions. This is going to get really hard. Right? And one of the sort of the big things that was really important for developing Spawn, as a big part of my personal research, has been trying to figure out how to do that cognitive control mechanism. That's sort of deciding what of many actions to do. And that's led us to a path where, as we start building up the model more complicated like this, the things that we've needed to implement just purely to do that task have turned out to look an awful lot like structures in the real mammalian brain, the basal ganglia and the thalamus, which is kind of nifty that those things come together. But that's going to be really important for scaling up to larger systems, is figuring out a good way of structuring this set of if statements and things like this. And it's going to turn out to be the starting point is going to be something like this, and then we're going to we'll give lectures on how to actually take things in that direction, and there's some fun papers. But the core idea starts here. But yes, this approach is very quickly going to get you to a point where this group of neurons is going to need to have tons and tons of inputs, and it's going to be highly nonlinear, and it'll be harder and harder to implement in this way. And so we're going to need to do something else. So think on that.
So that's a perfect segue to the next lecture, where we're going to actually focus on scaling. So we'll introduce a bunch of methods that make up the semantic pointer architecture. The basal ganglia, of course, is absolutely central to that entire architecture. And so hopefully people will join us once more for looking at going from these small kinds of models, but using exactly the same kind of components and building up to really, really, really crazy large models, as big as people have seen and built to this point, which I think is exciting and interesting. So with that,
sounds good.
say goodbye.
Thank you so much. Come back next time.